Hopefully this won't be too over. Shite.
All right, good afternoon, everybody. It's 3 o'clock, so I think we'll go ahead and get started. So the subject is building a faster web. So just a little bit of logistics up front. All right, so a little bit of logistics up front. There's going to be a lot of content in the slides. I will have a link at the end of the slides where you can see these online immediately afterwards. So don't worry about having to write down all the links and all the references and so on and so forth. Just watch and try to absorb, because I'm going to cover a lot of different tools. There's a lot of links that you can follow later and kind of dive deeper if you want to. So for now, just don't worry about scrambling to write everything down. Also, if you were at Arvin's session earlier today, there will be some overlap, but I don't think that's a bad thing, because frankly, performance is something we need to pay a lot more attention to, so it's worth repeating some of the points. So with that, I'm working with the Google team called Make the Web Fast, and it's a really interesting and fun project. So as you would imagine, at Google we spend a lot of time thinking about how to make our web apps fast, right? And a lot of teams come to us looking for expertise, help developing new tools, and best practices. But the larger mandate, which I think is what excites me and a lot of other people working on this team, is the actual goal for the team is to make the web fast as a whole. So we actually have a set of metrics by which we judge the performance of our team based on have we made the web faster, which is pretty amazing. And I have to tell you, it's a challenge to come up with those metrics and to actually make it faster, because frankly the developers are not making it easy for us. But that's why we're here, right? So we do a lot of work, anything from the kernel up, TCP/IP stack can be optimized that. Obviously things like Chrome, and then just front-end best practices. So let's take a look at some of the things that we've been working on. So first, there are some good constants that I think we all need to keep in mind. Right? Every month there's a new study that comes out and says, hey, we've lowered our page load time performance, we're a big e-commerce site, and we saw our conversions go up. And every time you read that, it's like, aha, I should make my site faster. But Jacob Nielsen published a really good study, or set of studies in a book on usability back in 1993. And he outlined kind of these high-level buckets. And the basic insight is, if an interaction happens within 100 milliseconds, basically most humans can't tell the difference, right? There's always going to be a bunch of kind of hardcore FPS shooters, gamers in the crowd will be like, I can tell the difference between a 30 and a 45 millisecond ping time. Like, don't even touch them. But for most web applications, the users won't be able to tell the difference within 100 milliseconds. It feels instant. 0 to 300, it's kind of an odd experience. When you find a button, it's sort of like it's a sticky button, right? Something's just not right. 300 to 1,000 milliseconds, unfortunately, that's a bug in the slide. That's a backwards timing tool there. It feels like the machine is working. Like you click the button and something is going on. And then at right about a second is that contextual switch that happens for a lot of users, where the computer's doing something for long enough such that you kind of start thinking about something else, right? You click the print button and all of a sudden you're like, oh yeah, I need to email Joe, and like I need to do that and that. And then if nothing happens within, let's say, 3 seconds, all of a sudden that little side foray that you took is already its own evolved line of thinking, and all of a sudden you've lost the user, right? So these are very good buckets to keep in mind. So now the question is, how are we doing? So we actually ran a study. We used Google Analytics to sample across a couple of billion sessions on mobile and desktop, and these are average numbers, right? And averages can be misleading, but they're still useful to just guide our conversation. And this is what we found. We found that the mean loading time for desktop is over 6 seconds. It's actually about 6.5 seconds. On mobile, it's over 10 seconds. And the mobile numbers are very, very optimistic, and we'll see one in a second. So in all actuality, they're probably much worse. And you can also see the distribution at the bottom, right? So the key takeaway here is it's slow. And if you're curious, you can follow the link here at the bottom later and actually look at, we did comparisons by country, by vertical, and a number of other dimensions. So there's work to be done here. And 6 seconds is unacceptable, I think. So one of the reasons could be, right, we could hypothesize that the pages are getting larger, and that is in fact the case. So we have another project called the HTTP archive, where we monitor the top sites across the net. We've been doing this since November 2010 and been aggregating this data, and we're actually planning to expand the data set for HTTP archive from tens of thousands of sites, which is what it's doing currently, to about 1 million sites by the end of the year, just to get a better sample. But the basic trend, you can see here. From November 2010 till today, both the size of the pages has increased and the number of requests. So the takeaway here is today, an average page weighs in just over, or just roughly at 1 megabyte. Isn't that amazing? 1 megabyte, that's your average page on the internet. And not only that, but it takes 84 requests to compose a page. That's a lot higher than what I expected those numbers to be. Now, here's a funny little thing that had me scratching my head for a while. An average page, an average HTML page takes 8 HTML pages. What? Iframes, right? We're including a lot of content, so these are the social buttons and all the rest. So that's why you have 8 HTML pages embedded in one page. You have images, and in fact, images clock in at 600 kilobytes on average, right? So there's a lot of work to be done there in terms of optimizing images and the rest. JavaScript, CSS, and out of all of that content, the HTML part of it is almost insignificant, right? It's 40 kilobytes out of 1 meg. So, this is the same thing, but it's slightly more visual, right? Because it helps to drive the point home. It's images and images. The second biggest one is scripts. So over the course of the last couple of years, we've pushed a lot of our logic into the front end, meaning JavaScript, and a lot of that execution is happening in the front end. And because of that, we're finding that a lot of the optimization nowadays needs to happen correspondingly in the front end. How you load those scripts, how you execute them, so on and so forth. So with that, let's think about what does it actually take to render a web page. So first, when you click on the link, so let's say we're actually on a given page and we're clicking on the link, the very first thing that needs to happen is we need to garbage collect the page. It seems obvious, but somebody needs to do it. And sometimes you actually run into an issue here where even just unloading the existing page, for example, if you have tons and tons of event listeners, before we can proceed, we need to garbage collect all of that stuff. And sometimes I've seen pages where that literally takes seconds. And you really have to scratch your head because you look at the profiler and it says, like, what are you doing? Nothing's showing up. It's actually garbage collecting the event listeners. Then there's the DNS resolution. We'll talk about that in a second, but it turns out, a lot of us don't tend to think about DNS, but it's a hidden cost that is actually a very real cost. And based on data we have, a lot of the requests are served, or a lot of the records are served with very short time to live. So in fact, it's not like you've looked at it once and you just have it for hours. It turns out 40% of all of the DNS lookups have to be refreshed every 5 minutes. So connection and TCP handshake, there are things that we can do in there to optimize that. We need to send the request. In fact, we need to send not 84 requests because hopefully we're using some connections, but still the browser will open on average 20 or 30 connections to render your page. Parsing the response, so on and so forth. So the key takeaway here, it's complicated, right? Like there's a lot of moving components in here. And each one of these little labels, black labels, we don't need to, we're not going to look into each one, but each one of these steps is a component that we need to take into account. And there's 3 major components in here. There's the user connectivity, so being on a fast internet connection, desktop versus mobile, 3G, 4G, so on and so forth, definitely makes a difference. And that's one thing that we can talk about. The second one is the actual server, right? If your server takes 10 seconds to render the page, that's a problem. A lot of people tend to focus, a lot of web developers tend to focus on the server component, disregarding the other 2. But certainly an important component. And then the last one is the browser execution. So what happens once you load that page, load the HTML, and all of a sudden you're starting to load all those JavaScript, scripts, CSS, and so forth. The key takeaway here is the user doesn't care, right? The web server can be really fast, but maybe your DNS server is dog slow. And maybe that's not something you've been thinking about today. What they care about is how long does it actually take for the entire page to render, not just how long did it take the HTML. You have your server logs, you're probably monitoring your server logs today, but are you monitoring your front-end performance? Probably not. And that's what you need to pay attention to. So a couple of things that our team specifically is working on. You know, some of the stuff is applicable to you as a user in your day-to-day life, and some of it is applicable as a web developer. So we found that on average, based on our Google crawl data, DNS resolution or lookup takes about 130 milliseconds, which is quite a long time. And a lot of people are surprised by that number because it's UDP, it fits into one packet, it should just be blazingly fast. Turns out a lot of the DNS servers are under-provisioned or just not capable of handling the load. So we have a project called Google Public DNS, which you can use. You can basically replace your own ISP's server with our DNS servers, and it turns out in many cases, not all cases, but in many cases, we will actually serve the response much faster because Google has a few servers around the world and kind of co-located strategically to answer these queries really, really fast. Then we actually have a couple of research projects for things like, hey, a TCP handshake requires a full round trip. Perhaps we could eliminate that. We actually have an IETF proposal for TCP fast open where we can send the request alongside with a TCP SYN request if you're familiar with the TCP stack. There's also things like congestion window changes. Turns out that most servers today are configured to start with a very small number of packets before the TCP window size increases. And we're proposing to change that to be much, much larger, to 10 segments instead of 3, which in our tests speeds up the rendering time by about 20%. Right? So these are the kinds of things that we're thinking about at Google, and in fact we've been deploying these things on Google servers and we've seen these performance improvements, and now we're trying to get IETF to adopt these changes. So for example, the C window changes are in the kernel, have been merged into the kernel, and you need to be running kernel 3.0 and later, and you'll get these settings by default. So some of these things, you just kind of inherit for free and you don't have to worry about it unless you are the sysadmin, at which point I should say, go upgrade your kernel and we'll just make stuff magically faster. Then there's things like SPDY, which is trying to augment HTTP. HTTP 1.1 is vintage 1999, right? Like the web has evolved quite a bit since then. We're serving a lot of small requests nowadays, JSON, small images, so on and so forth. And SPDY is one way that we can optimize for that. So one question I often get is like, hold on, like the web is just going to get faster. I'm just going to migrate from 3G to 4G to 5G to whatever, and like, it's all good. Not the case. There's two things we need to worry about. There's how much data you can push through the pipe, which is very important for video and other applications, but we have this hard limitation, which is the speed of light, damn it, and we can't go any faster, at least not that we know of today. And the issue with that is, remember the earlier slide where we said there is going to be 84 requests. Sometimes we'll reuse the connection, most of the time we can't. So there's 20 requests that need to happen where we need to do a full handshake, a TCP handshake, and then go back and forth and fetch those packets. That time adds up, right? So in fact, when we do the test, we see that after you reach about 5 megabits, your page loading time doesn't really improve at all, right? So I recently moved to a new location, and I found myself like completely obsessed about which data plan should I get because I want the fastest browsing experience. And then I realized that, hold on, it doesn't matter. Like, yes, sure, I watch online video, and having a fast connection really helps, but if I'm trying to optimize for fast pages, all I need is 5 megabytes or 5 megabits, and after that it doesn't really help at all. Like I'll get 2% improvement, but I won't be able to notice that. So that in itself means that we on the front end need to optimize how the pages are constructed. And the reason for this is, I've already described a few of them. TCP connections are expensive. TCP does have this thing called a slow start. It's not a bug, it's a feature. Right? It's, the basic idea there is we need to make sure that we don't overload the network. And I don't know the capacity of the link, so I'm going to start slow. And as I'm getting access from the other server, I'll start increasing my window until I get a congestion. Right? So it's just a way to be a good citizen on the net. But that actually works against us. Every time you open a new connection, you're starting slow, and it turns out that most connections don't reach their full capacity because a lot of times we're serving responses that are about 10 kilobytes in size. That only takes a couple of packets, so we've never used the full bandwidth of the link. So connection reuse is very, very important. And on average, we find that 1/3 of all the requests need a new TCP connection. And there are other studies by Akamai and others which show that on average, every HTTP connection serves about 2.5 objects. So, speaking of front-end experience, we have another tool that we maintain called webpagetest.org. If you guys are not familiar with it, you should definitely check it out. The first time you open the site, it'll look like it was something that was built in like 1995. That's a good thing. It was built by engineers. We definitely are in need of a designer. But there's a lot of great options in there which allow you to capture video and, rather capture video from any browser and see how the page loads. It can also give you a lot of metrics, optimization metrics. So I did this video just recently, and what I'm doing here, or what I wanted to do, is compare two newspapers. So Straits Times is a popular newspaper in Singapore, Guardian, I'm sure you guys are familiar with, and I ran this test from Tokyo. So specifically this was, I want to see how these pages compare in their loading time when they're loaded from Tokyo on IE8. So let me play this for you. So first couple of seconds, nothing. At about 3 seconds, 4 seconds in, we actually get some of the content. 8 seconds in, the ads pop up. At 11 seconds, Guardian is done, and Straits Times is going. And going. And still going. At this point, I thought it was a bug. Nope, there we go. So 25 seconds. So I want to show you something very, very interesting in here. So obviously the first thing you notice is the content comes in at about 4 seconds, right? So even though the images are still getting pulled up, if you're actually browsing the site, chances are you're already kind of browsing the headlines, you're interacting with the site, that's all good. Then let's skip right ahead and see, so what's happening in this 14 seconds to 21 or 22 seconds on Straits Times. Let me scroll back. So at 22 seconds, you can see in this area there's nothing, right? We're just waiting for content. At about 24 seconds, I think, or 25, an image pops up. And this is an image that is actually related to one of the stories on the site. And then something odd happens. Right after this image pops in, about a second later, it gets replaced with an ad. Now, I think that's a little bit bizarre because, at least in my experience, most of the ad code is actually optimized. Right? Like, that's what makes you money. And usually there's good testing practices and test suites and everything for this kind of stuff. So there's actually another problem here, which is this specific image is actually blocking the rendering of the ad. The ad takes less than a second to come in once it's unblocked. But this image is blocking all of the ad rendering. So this has an enormous, I'm going to make a hypothesis, this must have an enormous impact on the view rate, on the click rate, on everything of the ads of this newspaper, right? So this is a video that you can get. Web Page Test actually composites the videos for you. You can compare multiple sites. One of the best tools that I have to just showcase people why you should think about front-end performance, because you have to catch things like this. So just a quick recap, faster connectivity won't help us. Going from 3G to 4G, I think a lot of users were somewhat disappointed that all of a sudden their mobile phone is not loading everything 3 times as fast. The phone is faster, which helps, but we're up against the bandwidth limits or the speed of light limits, so we need to do better. So the good news is this diagram that I showed you before is actually part of a new spec, a W3C spec called navigation timing. So Google and a number of other companies have been working together to come up with this. And each one of these labels here is actually a timer that the browser makes available for you. So until very recently, in fact, a year ago, we could have been standing here and I just couldn't tell you how you actually get something like the DNS resolution time in your browser. It was impossible. But the good news is today, there's already good support for navigation timing across most of the browsers. So the way to get at it is, if you're using Chrome or similar, you can open your console and you can just type in performance.timing and you get this object back called performance timing, and it'll just have a whole bunch of labels with, I think I'm getting some feedback here, a whole bunch of labels with microsecond level granularity. So this is available on every request, and this is for this specific page that you've loaded. Right? So you can actually figure out this request happened, how long did the DNS take, how long did the redirect take, how long did the other aspects of this page take. So now that you have this, and this is available within the browser to the client, you can actually gather this data from the client, right? You can grab this object, serialize it as JSON, push it to your own server, and analyze it there. The good news is we have IE, Firefox, and Chrome that already have it implemented, so you can use it today. Safari and Opera are still lagging behind and haven't implemented it, and Android browser has it today. So when I said that when we looked at the mobile data, in fact, the way we've gathered that data for Google Analytics is we use the navigation timing from the browser, right? And when I said that the mobile data is probably very optimistic, it's because we're only gathering the data from the Android browser, and if you're running the 4.0 browser, chances are you're on a pretty modern device. You have dual cores, plenty of memory, so on and so forth. So older devices will have slower experiences, and chances are you're on a good network to begin with, because if you have one of the latest Android devices, chances are you're going to be on a good network. So the good news is we also implemented support for navigation timing within Google Analytics. This is something that very few people know, but it's extremely useful. And here's just a little quick tip. The way we're gathering the timing data is we sample. We don't collect this data from everybody, because frankly that'd be a lot of data. There's two flags. Google Analytics by default, if you just don't do anything, will gather this data from about 5% of your visitors, up to a maximum of 10,000 visits per day. But if you have a small site, if you get less than 10,000 visitors per day, you can actually override it and just say sample for everybody, because I know I'm not going to get 10,000 visits a day. So that's what I'm doing here by saying set site speed sample rate to 100%. So if it's on my site, then just gather every data point such that I have more data. So what does this give us? You can actually navigate to your existing Google Analytics, and you'll get all of this timing data inside. So there's, for the period that we're looking at here, 60,000 page views. This just happens to be my own site. Average page loading time is 9.7 seconds. So here I am preaching about making the web fast and fast pages, but apparently I got some work to do myself. And let's not talk about the 50-second load time there. Just pretend like it's not there. But I think there's a very good lesson in here, which is if you look at these numbers here, so there's redirection time, DNS time, server connection time, server response time, and the download time, right? If you add up these numbers, there's maybe a second in there, but then my average page loading time is 9.7. Like, what the hell is going on there, right? There's another 9 or 8 seconds lost somewhere. And in fact, they're not lost, it's all front-end time, and I'll show you in a second why the discrepancy. So another thing that I think a lot of people miss, and I'd really like to point this out, is you have all of the power of Google Analytics within these reports, which means you can segment by any of the attributes or the dimensions within Google Analytics. And I don't know if the demo and the Wi-Fi gods are with us today, but I'm actually going to attempt this. Let's see if this works. So this is just my own account. This is live GA. You have access to this today, and so my file is come on. Maybe. Maybe not. It's actually very hard to tell if it works or not because you get this. Oh, there you go. All right. So we're looking at this account, and one of the things I want to show you guys is advanced segments, because even though the name says advanced, it's actually very simple and it's incredibly useful. So what you can do in advanced segments is you can, well, segment the visitor data based on any number of dimensions, right? So I have a couple of predefined segments, but I'm going to create a new one. And what I want to do is actually look at the, so I want to compare city, which is San Francisco. And I'm going to add a dimension, mobile. So I want to find all of the visitors coming to my site from San Francisco that are on a mobile phone or on a mobile platform. Right, so I can, let's give this a name. This is mobile, and save the segment. And here it is, right? I'll actually enable some other segments just so we can see the difference. I also have Singapore. I'll compare it to a desktop version. Actually, we can compare it to all three. Hit apply. And now we can see the average timing data across each one of these segments. So we can do things like, let me segment out all of the IE users from all of the Firefox users, all of the Chrome users, all of the specific version of a browser users, or by continent, by city. And you can compare mobile versus desktop, so on and so forth. There's a lot of power that you have in here. And then, let me hit back. Once you have this data, you can actually drill in, and I took the snapshot just to show you something, which is, remember that 50-second load time? Turns out, if I just do some very crude segmentation, I can find that this spike here, even though it skewed the entire average, really it was coming from Asia, right? And so North America was, whatever happened there, North America was fine, but for some reason, there's actually a part of Asia that was unable to load one of the social buttons that I had on my site. And the script just happens to have timed out after 50 seconds. Right? So it had nothing to do with my site. It just, there's some routing problem somewhere, and I think it was actually, I tracked it down to a Twitter button. And Twitter was not loading for some period of time in Asia. But using this tool, you can actually figure this out. So another point that I think is very, very important is, if you look at these reports, it's all about averages. Averages are great, but they often lie, because if you spend your time thinking about performance, you know that you need to look at the actual distribution of the data. And we actually do provide the underlying distributions within Google Analytics. If you head back here, that's actually under the technical tab, performance technical, and you'll get these distributions where you can see interesting trends. So this is just a quick case study that I put together. This is once again based on my own site. It just so happens that earlier this year in January, I migrated my site to a completely new hosting provider. I changed the design. I was on WordPress. Now it's a statically hosted site. So there's a whole bunch of changes. And what I'm showing you here is a distribution. One is for December 1st to December 31st. So this is my WordPress site, and this is the new site. And you can see that the distribution changes, right? It shifts. First of all, it's a skewed distribution. It's not a normal distribution, right? Because there's a tail. And second, the actual distribution shifts up, which shows that all the changes that are applied actually did make the site faster, right? And this is page loading time. So for many users, they get this 1 to 3 second time experience. So that's, you kind of expect to see this. Here's the far more interesting example of what is the average of this distribution. Well, it turns out if you actually do the math, it's, let's say about 3 seconds. But the average completely obscures the point that this graph shows, which is, in both cases, it's actually a bimodal distribution, and there's actually a very good reason for it in this case. Here, this is once again a WordPress site. I did have caching, right? If the page was in the cache, in the memcache in this case, it was served pretty quickly, within 100 to 500 milliseconds. But then every once in a while, I would get a cache miss. I would have to go to a database, fetch the page, and there's a delay, right? So that's why you have kind of this big gap. In this case, very similar, but no caching here. It's probably either it's in the file system cache or it has to fetch it first from disk, or fetch the metadata from disk. So this is why you should really pay attention to these underlying distributions. They can tell you a lot of interesting stories about the performance of your site. You'll find some users where the average will say it's 30 seconds, but then you'll find that it's actually just a couple of people on the tail end for whom the performance is really, really bad for whatever reason, and it's just skewing the entire distribution. So that's cool. After we did this work, we actually decided to, hey, we can actually enable this as a feature within Google Analytics, such that you can push any sort of timing data into Google Analytics. So we have this new interface, and we just released this a couple of weeks ago, called Track Timing, or a new API, I should say, which allows you to pass in a category, a label, and a time variable. And we'll actually aggregate that data and give you all of the same time series analytics. So you can use it for things like, hey, I'm loading an async resource, right, like jQuery, and I want to time how long that takes, or I'm making an outbound request, an AJAX request to one of our servers. You can do that. I'm actually abusing this API to do something completely non-site speed related, which is, these are HTML slides. I share them, I'll share them with you guys. As you guys browse through the slides, I'm actually keeping track of how long you spend on each slide, just to provide myself with a little bit of analytics for, hey, a lot of people have spent a lot of time on this specific slide. Maybe it's confusing, or maybe because it's amazing, I don't know, but it's a signal. So you can use this data for anything you want. It just happens to live within the site speed reports, but please don't constrain it to just that use case. So that was navigation timing. There is another spec in the works called resource timing. So navigation timing gives you all of the data for the actual first HTML request, or that's the first page. But as we saw, every page loads a lot of sub-resources, and it would be nice to have that same data for each sub-resource, right? So if my browser is opening connection to the Akamai CDN to fetch, I don't know, a version of jQuery, I want to know the DNS time and all the rest. That's what resource timing is for. It's coming, and it will be here soon, definitely sometime this year. So just a quick recap, user-perceived latency. That's probably one of that is the #1 thing that we've learned in the past year, just within Google, helping optimize pages for Google products. You really have to think about user-perceived latency. Navigation timing it's in many ways changed how we can approach it, because previously we just didn't have access to this data. We happen to like GA advanced segments because they give us a lot of power to slice and dice that data. And then you can actually set up very simply reports within Google Analytics, just to email you automatic reports once a week or once a day, just so you can kind of keep tabs on, hey, my DNS is performing well, or there's a problem in Asia. Things like that. All right, so now getting to more of the hands-on, right? So we have a lot of tooling in the browser that help us optimize the pages. And here's a quick question. How many people can tell me what the blue and the red lines are? Onload. Okay, so I think there was another 1 or 2 hands that came up when I asked that question. So these are 2 very, very important metrics that you should keep track of, right? So you have the waterfall, which shows you how the page is broken down, but the 2 lines that are displayed in here show you 2 kind of key points in the rendering cycle of the page. The blue line is DOM content loaded, and what this tells you is the browser has finished parsing the HTML. The page is technically marked as it's now interactive, but then the other execution begins. And onload fires when all the resources finish. Onload is when that spinner stops, right? The page is technically done. You can still be loading JavaScript, but at least the browser tells you that the spinner has stopped. And as you heard in one of the previous presentations, we find that a lot of users correlate that spinner, even though nothing's changing on the page. Think about the Singapore Times newspaper. That page was effectively static for 10 seconds because that image was loading, but the spinner was going. So a lot of times I would just sit there and be like, I'm not sure what's going on, I gotta wait. So these are two very important things they should keep in mind. Put your CSS at the top, JavaScript at the bottom, or defer it. So this is basically the difference, right? If you look at CNN, down content loaded fires at about 4.5 seconds, which means that we've laid out the actual content. The CSS has been applied, the text is there, and then document complete fires at 10 seconds, which means we've loaded all the pages, we've loaded the JavaScript, and all the rest. So for a lot of users, they'll already start interacting with their page at this point. And just comparing these two numbers between different pages can tell you a lot about how the page is structured. Because you'll find when people don't defer or async loads their JavaScript, you'll find that the document complete fires 30 seconds in, which is a terrible, terrible experience for a lot of users. So how many people can tell me the difference between these three scenarios? Okay, so we got 2 hands. All right, good, we're learning a lot. So I'll zoom in just because it's a little bit hard to see. There's 3 cases, and I think most everybody will be familiar with the first one. You're just loading a script. So what happens when the parser hits the script? It sees the stack, says, okay, stop the world, I need to download this thing, right? Let me dispatch a network request. That's this blue component here. Once I've fetched the content, I'm going to execute it. Once I've executed and I've applied all the logic, I'm going to continue parsing. Right, so if you have 10 scripts sitting at the top, this is what it's going to do. The browsers today are doing kind of speculative prefetching and other things, but for all intents and purposes, this is how your browser will behave. When you specify the defer keyword, which by the way has been in the spec and implemented since IE8, so this thing has been here for a long, long time, it's just we haven't made good use of it. What it says is, I promise that I won't use document.write, and I won't do all these bad things. But what you can do is go download the script in the background, continue the actual execution or the parsing of the page, and then execute it right before you fire the onload. And one nice property that a lot of people like about defer is it preserves the order of the script. So if you have script B and then script C, and script C said also defer, you basically guaranteed, with a delta of different browsers to different things, that B will be executed before C, which is sometimes important. And finally, async, which is the new keyword that's been added just recently and has actually pretty good support for, basically says, go download this thing, and then whenever you have it, just execute it. So the most important thing here is you're eliminating the wait for the network, which is actually quite significant, right? That could be 150, 200, 300 milliseconds to fetch a resource. So if you're not using defer or async, please take a look at your JavaScript. This alone can help you save 20–30% of your loading time just by deferring this keyword.
Why would you not want to use async?
Why would you not want to use async? So you have to. So once you start applying everything in async, or once you start applying async to everything, let's say you have order dependence. All right. So B needs to be loaded before C. Async just says whenever you have it, just load it. So that doesn't mean that you shouldn't be using async, but it means that now that you need to apply some extra logic, or perhaps change your logic such that these things are loaded in the right order. So there are script loaders out there that do this for you. I think Modernizer, Require.js, and others already kind of implement these patterns under the hood. But do take a look at defer and async and just try and apply it on your site. Or take a look at some script loaders. Now, once you've actually parsed the script, you can actually go into the timeline view, which I don't think a lot of people use today, or a lot of web developers use today, but if you go to your timeline view and you hit record and you let the script render, or you'll let the page render, you can then actually navigate into any one of the given scripts and see what it triggered. Right? So for example, executing a script can execute a lot of CSS reflows, which is just pauses the actual rendering time. You can get a lot of information from this view for things like how many timers has it set, and so on and so forth. When I did this, this is actually a profile from CNN.com. I opened one of their scripts, and for whatever reason, one of the scripts was setting something on the order of 400 timers when it was executed. And I have no idea, I didn't bother to look at it, just kind of went back in shock. There's a lot of good stuff that you can find in there. So, switching gears, 60% of the weight on the page is images, right? And this is more just a public service announcement. Portable network graphics does not mean that every graphic that you put on the network needs to be a PNG, right? I think there's some confusion in there. And just to prove the point, 4 different images here of a Chrome logo. This is a PNG. This is a crushed PNG. This is a JPEG, and this is a JPEG with quality of 80. Now, if you have really sharp eyesight, you'll actually notice some artifacts on this thing. But this JPEG at 100, visually there is no difference, and it's about 3 times smaller than the PNG. So there is lossless and lossy compression. There's a big difference there. What about SVG? Good question. Probably even faster. Although you're trading CPU time there. So the key takeaway here is optimize your images. And the right thing to do is automate the solution. There are very, very good tools out there. There's web tools like Smush It by Yahoo. There's PNG Crush and others, which are basically tools that you can run as a deployment step, which will automatically apply optimization on top of your images. Right? So if you're saving a lot of PNGs, and I know I'm guilty of this, whenever I write a blog post, I'll just save everything as PNGs. But thankfully, I have something on the front end that looks at the PNG and says, hey, this is actually better served as a JPEG. Let me optimize it such that when it's served to the user, it's automatically in the best format. And incidentally, we also have a project called WebP at Google, which in our experiments allows us to get about 20% improvement on the actual image size on top of the JPEG compression. So Chrome is the only one that supports WebP, but if you have kind of an automagic optimizer in the front that is able to distinguish based on user agent, perhaps you could be serving WebP and save another 20% on top of those 600 kilobytes, which is actually a significant amount of data. So, we talked about navigation timing. There's Google Analytics. Pay attention to your onload. Image optimization is a big, big deal, especially in mobile. And Chrome DevTools. There's a lot of good stuff in there. And just as a little bit of an aside, I don't think a lot of people realize this or know this, but Chrome DevTools is a web app by itself. And just to prove the point, I'll show you a quick demo. So what I have is, I'm running this presentation in Chrome, and I'm going to start another instance. And you can see that I'm passing this special flag called remote debugging port 9222. So Chrome ships with a remote debugger, but it's disabled by default for security reasons. So if you want to run this, you just have to pass it this flag, and we now have Chrome Canary running here. So what I'm going to do is, I'll go to this page, just resize it. Browser, open there. We've lost our other browser. That's clever. There, minimize it. All right, there we go. Just very slow. So what I'm going to do is I'm going to go to port 9222. So these are two different browsers, and you can see that I'm just accessing this other browser on port 922, and if I click into this tab here, I get the Chrome developer tools. And the cool thing is this is actually the developer tools for the page you see on the left. So as I browse over the elements here in the other browser, you can see that they're being selected in the other browser. And not only that, but you can also have the full capabilities of all the things you're familiar with inside. So for example, I can just right click on this thing, and I can delete the entire node and modify it. I can set JavaScript debug points. I can go into the network tab, and I can go here and reload this page, and you see that I get the network waterfall. So this is the exact same tools that you have. And just to prove the point that this is a web app, there's nothing magical here. I can, in fact, open the developer tools on the developer tools. Let me close the JavaScript debugger here. I'll be like, you know what? This network thing, yeah, don't like it. All right, so gone. So how does this work, right? So Chrome Developer Tools is a web app. How does this work? Let me go back here. We have this other endpoint called /JSON, and what it gives you is a list of all of the open tabs, and each one of the tabs has this extra parameter called WebSocket debugger URL. So all of the data that you see in Chrome Developer Tools is in fact being propagated over WebSocket, and this web app is just listening to it and subscribing to all the events and kind of rendering a nice visual representation of the tree. So that also means that you can start building interesting tools like server-side tools, right? It's just a WebSocket. So I can actually have this script here, which connects to the localhost 922. It grabs the first open socket and just says, by the way, I want to track network data, right? So enable delivery of network events to me, and please navigate yourself to Twitter and search for Chrome, right? And then just spit stuff out to the console. So just move this to the right. And if the network, oh, I know why. One instance of this thing open. It's this client. There you go, and there's a lot of scrolling text. What it shows you is the actual events, so things like data, I just received data, request ID, so on and so forth. So you can drive and control Chrome. You can set debug points through your CLI. You can build and start building a lot of interesting tools. And actually, this is what we're doing quite a bit within Google right now. Just trying to figure out how can we automate and drive Chrome, because you get the full power of Chrome, plus all the debugging capabilities right from the command line. So lots of interesting stuff. So let's actually look at that. Go back to here. So each tab has a debugger URL. You can connect to it. You can get tons and tons of data. This is what we just saw. Once again, enable network. And we actually have and recently published the 1.0 of this spec. So it's going to be there, it's going to be stable, so you can now start building kind of tools and expect that they will actually continue to work for at least the foreseeable future. So here's an example of a sample event that I just recorded there. Right? It actually contains quite a bit of metadata. This specific request was an XHR, so it's an AJAX request, It got 200 response. This was for trends on Twitter. New connection open, so you can actually check when the new connections are being created. No cache, so when you have all of the timing data. So lots of detailed metadata available in here for better tools to be built. Why am I showing you all this? Well, we also have Chrome for Android, right, which is the beta browser. The cool thing about it is you can tether your phone to your laptop via USB, and then you can open this debugger on your machine, just like I did here, and get all of the network activity data, debugger, set the debug points, do anything you want right from your web browser, which is huge, right? If you're developing mobile applications, you know how painful it is to debug those things today. It's nearly impossible. So this is beautiful. Now, changing gears once again, we have another project called Google PageSpeed, and there's two big branches in here. One is Insight, and one is the automatic or automate and optimization part. Insight is a web tool where we're applying a whole bunch of heuristics and rules to figure out how can we help you optimize your pages. Right? There's a lot of things you can do to your pages. So we have about 31 rules, and here's an example. We have CNN. I'm just running CNN.com through our Insights tool. It's free. You can use it today for any page. And we'll tell you things like, hey, we found that there's